Good morning, everybody. This video is going to take us through a little bit more involved situations of torque, building off of what we were doing in class yesterday. I'm going to go relatively quickly through these different examples and talk through each one. At any point, feel free to pause, go back. You'll see me right through each of the examples as we go. Having a calculator out in the meantime as I'm going through each one of these and pausing is probably good practice, good idea as we go. When we're all done with this video, you guys will get into your lab groups and do the second lab involving torque as we go through this today. So the first thing, as we talk with torque, I went through some examples in class yesterday and used the term levers quite a bit. Our own bodies have a lot of different levers to them. Any joints that you have can serve as pivot points. Your arms, your fingers, your feet, your toes, your legs, etc., can all serve as levers to lift things, to move things, and that's what's being demonstrated and shown. What you're seeing more than anything else here are just all the different forces that can be incorporated with just about anything that you do to lift things, to move things, like we were talking about. So showing a little bit more of the practicality of some of the things that we're talking about here beyond just what we did yesterday. Now, what we're going to focus on is this concept of equilibrium, and I know that I talked quite a bit about this at the end yesterday, but as we go through these next few slides, there are some different situations that we're going to encounter, and these bullet points listed here are going to be the things that you will need on each of these problems so that you don't lose track of information. I highly recommend having some kind of diagram or picture that goes with your problems that you're doing. As far as a picture goes, you'll see my example. They're nothing fancy, but they have all the information that we're going to need on them. You got to have arrows showing which direction the forces are going, and you need to label the lever arm and what we mean again by lever arm, just going back to yesterday, distance that the force or the mass is from the pivot point. And you got to have the pivot point on there somewhere too, because otherwise we don't have a reference for anything. So those are some key things as we go. The first couple will be relatively simple. I think there are 4 in total that we'll talk and go through here, just giving you a sense of some different situations and examples all the way through. So here's the first one. It says, how much force does it take to lift a meter stick with a tape dispenser centered on it if the meter stick is 10 newtons and the tape dispenser is 50 newtons? So here's what I'm going to do with this diagram down below. First, I am lifting. So if you see where the hand is, that's going to be my force acting up. That ultimately right there is my unknown. Now the distance to get to that, since we're told this is a meter stick, we know it is going to be 1 meter. Now what is it that I'm lifting? I'm lifting a tape dispenser that weighs 50 newtons, but I'm also lifting a meter stick, which weighs 10 newtons. So what I'm going to do is I'm going to draw a force halfway, and it's going to be 60 newtons. It's the combination of the two. Since they're centered, I have to include the weight of the meter stick. We didn't do this in the lab yesterday because the meter stick's center of gravity, center of mass, was at the pivot point. Now that our pivot point is all the way over here at the far end, it's being lifted as well. So we have to include it. And the distance there is going to be 0.5 meters. So when I set up my equation, the two sides, if you will, are going to be what is being lifted versus, or what force is acting upwards versus what forces are acting downwards. Now, I know we talked a lot about rotation. You could also look at this from the standpoint of counterclockwise and clockwise. Up and down, I think, tends to be a little bit easier. So that's what I'm going to be using here. So my F that I'm looking for times distance 1 meter is going to be equal to my 60 newtons times 0.5 meters. So when I go through and do that, I end up dividing both sides simply by 1 meter. Those will cancel. And F, my unknown, what force do I need to apply? 60 times 0.5 is just simply 30 newtons. Divided by that 1 meter is just dividing by 1. So I'd have to apply 30 newtons to lift that 60 newtons worth of stuff sitting in the middle. Our second example, same stuff, however, we're taking the tape dispenser and putting it off center just a little bit. So this is going to change things. So let's talk through what's going on. First, much like before, we have our force that we are applying over here at a distance from the pivot point, once again, of 1 meter. Now, I'm going to start with the meter stick. The meter stick weighs 10 newtons. And I'm going to still put that in the center of the screen, on the center of this thing, because, and I'm going to include our 0.5 meters here as well, because the meter stick is being lifted. The center of mass, or center of gravity, of the meter stick is at the halfway mark, the 50 centimeter or 0.5 meter mark. So we still have to account for that. The previous one, we did that alongside the tape dispenser. This time we're going to have it serve as its own separate thing. Now, the tape dispenser has a force, a weight of 50 newtons, and we're told up in the problem that it's 20 centimeters from the pivot point. 20 centimeters would be 0.2 meters, so that's what I'm going to include there. Now, as I said, when we set up our equation, upward forces on one side, downward forces on the other side. So I'm going to just go with F times 1 meter equals, and then I'm going to put it in parentheses to separate it out, 10 newtons times 0.5 meters for the meter stick plus 50 newtons times 0.2 meters for the tape dispenser. So, and then what I would do, of course, since it's only 1 meter, it's really not going to make a difference as far as the calculation goes, but I'm still going to write it out here. So I now have, this is my remaining. 10 newtons times 0.5 would be 5 newton meters plus 50 times 0.2, which would be 10 newton meters. And then dividing by 1, I end up with 15. The meters are going to cancel out, so the force I would have to apply to lift this would be 15 newtons. I've taken the heavier stuff and moved it further away from me. That's basically the pattern that you're going to begin to notice with this. So, our next one. Now this is going to look really different, but once I go through it, I think you'll see how this will work. So we have two guys here, Tyler and Jake, carrying a pile of physics books on a meter stick. Meter stick, once again, like we've been using, 10 newtons weight. Books are placed right in the middle, and they weigh 250 newtons. We want to know this time now, how much force does each person exert? So here's how we're going to go about doing this one. we're going to make this Tyler on the left and Jake on the right. The way I'm going to set this up is I'm going to actually make Tyler into our pivot point, and I'm going to ignore him for now. And I'm only going to be worried about what is Jake doing over here at 1 meter distance, just like before, at a 1 meter distance. So I'll actually even start my equation right now. F times 1 meter, that's going to be the upward force. The downward force is going to be a lot like the first problem that we went through earlier. I'm going to have a downward force here of 10 newtons plus 250 newtons for the stack of books. So it's going to be 260 newtons at a distance of 0.5 meters. So I'm going to put that in down here. So once again, divide by the 1 meter. My force is going to end up being 260 times 0.5, or 130 newtons. Now, this question ultimately asked, how much force does each person exert? And I said, for the time being, and going through this, I'm going to ignore Tyler and just focus on Jake on the right. Well, how do we find the other unknown? There are ultimately two methods. One is I can go back and do everything I just did and just simply switch the pivot point and go back through the whole thing. Or I can recognize that the total weight was 260 newtons. And if that thing is balanced, the total weight upwards has to be 260 newtons. If Jake exerted 130, Tyler would have to exert 130. They would add up and equal out. And that's all I really have to do. So, bring to the final one. Same two guys here, except we now have our books off center. It's the same setup. I'm going to start with Tyler as my pivot point on the left, Jake on the right. We're going to have his force up as our unknown, 1 meter away. And then we will have our meter stick of 10 newtons, half a meter away. And then we will have our stack of textbooks at 250 newtons, at a distance of 0.25 meters. So our equation will look like this. 10 newtons times 0.5 meters for our meter stick, and 250 newtons times 0.25 meters for the books. Once again, divide both sides by 1. So F will end up being 5 Newton meters plus 250 times 0.25, which would be 62.5 Newton meters. Divide that by the 1. We get 67.5 newtons. That's how much force Jake will exert. So how much would Tyler exert? I'll move that up here just so we can see it. We know the total weight of everything is 260. If I subtract 67.5, that's going to get me my answer of 192.5. Now that should make some sense that Tyler's got to exert more. The books are closer to him in this situation. This would be like if we're doing a dual lift of something very heavy. If it's perfectly balanced, we both would exert the same. If the bulk of what we're lifting is closer to one person, they're going to have to lift with a greater amount of force. So that takes us through the different examples and situations of what we call the advanced versions of the sub is going to give you some more specific instructions as far as the lab today goes, but you are going to be getting into your lab groups once everybody has gotten through the video, and you're going to be working on a lab called Keeping in Balance. You'll use all the same equipment that you did yesterday, except your unknowns today. There are two parts. You have an unknown object, and your task is to figure out what is the mass of that object. There will be a scale up front on one of the tables for you to grab. But part one is going to be using your equipment, the masses that you have, to figure out what is the mass of the unknown object. And part two is going to be figuring out the mass of the actual meter stick that you are using. So the one thing I want to show you with that, if you're tasked with trying to find the mass of the actual meter stick, what you're going to do is you're going to have some amount of mass on one side here, and I believe your pivot point is going to be at 0.85 meters. You're going to have some mass that balances your meter stick, and take note, over here there is nothing hanging over here at all. You're just going to get the meter stick to balance itself out, so it's level. There is a force or a mass on that side, and it's the mass of the meter stick. The center of gravity, center of mass location of your meter stick should be about at the 50 centimeter or 0.5 meter mark. Now, yours, it may not be exactly that. If you remember yesterday, some of you had to balance out your meter stick because at the 50 centimeter mark it wasn't balanced. Get it balanced and use the mark where it is indeed balanced. If it's 51 centimeter mark, use that. Okay? Now, here's what that means. The force acting down, or the mass of the meter stick, is going to be located at this point, whatever that ends up being. That lever arm is going to be roughly 35 centimeters. Again, if yours is at 51, then it's going to be 34 centimeters. That's a very important detail to pay attention to. Okay. So you'll ultimately get it balanced out. That lever arm distance from the pivot point at 0.85 or 85 centimeters, and the lever arm out to your meter stick is going to be somewhere around 35 centimeters. You can, when you test this all out, there's a scale, as I said up front, for both your unknown mass, but also for your meter stick to get the actual mass. You'll be asked to do a percent error at the end, but those are the two parts to this particular experiment today. So the sub will give you any additional details that are needed, but you'll have the class time to work until the last 15 minutes or so when you take the quiz today. Good luck with the lab, and I look forward to seeing everybody again tomorrow.